Repeating non-terminating decimals. We shall solve problems which appear to be not related to geometric series, but these are problems that can be modeled after a geometric sequence and a geometric series. Example 2.22. Converting repeating non-terminating decimals to fractions. Convert the repeating non-terminating decimal 0.121212 to infinity into rational form in lowest terms. You know that this number is a rational number. It is non-terminating, okay, but it is repeating. So that means this is a rational number. And any rational number can be written as a ratio of integers. So that is our goal. We shall write this repeating non-terminating decimal into a rational form. What is the rational form of this decimal number? We can look at this repeating non-terminating decimal as a sum of a sequence of decimal numbers. Look at this. 0.12 plus 0.0012 plus 0.000012 again, plus 0.00000012, so on and so forth. And if you were to continue with this addition, you will produce this. You will produce this non-terminating but repeating decimal number. Each of this is a term in a geometric sequence. But when we add them term by term, what we produce is a geometric series. So this is a series. You can now see our goal. Our goal is to look for the sum. What is the sum of this geometric series? So if we were now to add the terms of that sequence one by one, we will produce a sequence of partial sums, and that is what we call our geometric series. Now pay attention to this. 0.12 can be written as 12 over 100 plus 0.0012, that is the same as 12 10,000ths, so on and so forth. And we can factor out 1 over 100 here, and this is what we came up. 12 times 1 over 100 raised to 1 plus 12 times 1 over 100 raised to 2, so on and so forth. So the form of a geometric sequence that we are familiar with is revealing itself now. The general term is given by a sub n is equal to 12 times 1 over 100 raised to n. And so our concern now is to look for the sum of this geometric series. Does it even have a sum? Yes, it has a finite sum because the common ratio is less than 1. That finite sum is the rational form of this non-terminating repeating decimal number. Let us now obtain the sum of this geometric series. In the notation for a geometric series using your summation notation, this is how you write it. This geometric series converges to a sum, to a finite sum, because the common ratio is less than 1. What is that sum? This is the sum. The first term, okay, so you evaluate the term when j is equal to 1. That is the first term. And it's equal to 12 over 100 divided by 1 minus r. So let us simplify this. 12 over 100 divided by 99 over 100 is this. It's the same as this. 12 over 100 times 100 over 99. We cancel 100 and we are left with 12 over 99. But this is not yet in lowest terms. So there is a common factor which is 3. We cancel 3 and we are left with 4 over 33. So this is the rational form of this non-terminating decimal number. So what this means is, if we have a calculator right now and if we press these numbers, we ought to see this decimal number. Okay, so I will now get a calculator and we shall press these numbers. Let us see the result when we divide 4 by 33. 4 divided by 33 is that. Okay, we got it right.